Okay. Hello, everybody. I hope that you are having a wonderful day so far. Welcome to freemathhelp.ca. If this is your first time joining, um, I just want to say hello. My name is Arlinda. I am the CEO at Scholarly Elite Tutoring. I don't tutor myself. I don't personally tutor anymore, but I have been a tutor for many, many years and I have tutored hundreds of students. So that's kind of a little bit about me. I hope you guys are having a great week so far and that distance learning has been going well for you this week. I know that those of you who are in math class right now might have some questions that you'd like us to address, and so you're more than welcome to leave those in the chat. That's really the whole purpose of this live stream, is to provide you guys with a forum where you can ask your questions, and also to provide some lessons that are a little bit more interactive than just watching a video, because you can ask questions as I'm going along. So without further ado, today we are actually going to take a break from what we've been doing these past couple weeks, which was trigonometry. I know I said we were going to do trigonometric graphs today, but to be honest with you, my brain hurts today. I have a bit of a migraine, or I'm starting to get a migraine, so we're actually going to do something that involves me thinking a little bit less, and that is radicals. Now, for those of you who have been in grade 11 and have already done radicals, this will be a nice refresher for you. And if you haven't, I'm going to kind of start from ground zero and work our way up to kind of give us a better idea of what they are. So radical expressions really are expressions that kind of just look like, oh, why is this not working? There we go. They look like square roots. So for example, you'll have something like this. Let's say 8, and this is a radical. So obviously this is a square root and we're used to seeing that, but things get a little bit more complicated because with radical expressions, you have certain operations and the way that they work is very specific. So it's important to understand how we can break these down and what is allowed and what isn't allowed. One important thing to note about radicals, and if I could just get my paperwork here, there we go. It's really important with radicals, like for example, you have your entire radicals, which is what this is right here. This is an entire radical. And every time I say the word radical, I just think of the guy, the bus driver from The Simpsons, that always says, "Radical dude." I don't know why, but that's just how my brain works. So that's an entire radical right there. And we also have mixed radicals, and they look like this. They'll have a number in front of them. So 2 root 3, that's a mixed radical. I'll give you another example of an entire radical, such as 16, root of 16. Another example of a mixed radical is 4 root 5. So the 4 and the 2 are coefficients. Now, the reason why we leave radicals the way they are, and actually radicals are a very important skill because these are things that you will actually use if you're going into the sciences. These are the pretty much kind of the most correct way to leave final answers. As I've mentioned many times before during freemathhelp.ca live streams, decimals are actually not the most accurate or correct way of representing numbers. And what that means is that if we can reduce a number down to its very, 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 simplified form, typically it's going to be simplified either as a radical expression or as a fraction expression. And it's really important to understand how you simplify these particular things. So we can change mixed radicals into entire radicals, but before I show you guys how to do that, what I want to show you is first how we simplify entire radicals. So I'm just going to erase this here, you guys. Something about this eraser function is so satisfying, I can't even express to you. Okay, so let's talk about entire radicals. Obviously, if I was to just plug in the square root of 8, I'm going to get some crazy decimal. And we don't really want to do that. Now, the way that this works is that obviously we can further break down our radicals into more simplified versions of what they are. So I'll show you guys what I mean. This can be broken down further, and it looks like this, because 8 does equal 4 times 2. And what I always want to do when I'm simplifying radicals is to actually simplify them in terms of perfect squares. So we know that 4 is a perfect square because it's 2 times 2 equals 4. And the way that that helps us is the following. So this got simplified into root of 4 times 2, and then this actually can be broken up like this. Root of 4 times the root of 2. And actually, if you work backwards, you'll see that that's true. No matter how you slice this, it's saying the same dang thing. And that's actually really helpful for us because it does show us how we can reduce this further. So now we break this down more. So we know that the square root of 4 is 2 because the whole goal of this was to get a perfect square in there. And then I also know that if I was to square root the number 2, I'm going to get some insane number. And I don't want that. So I'm just going to leave this as it is, the root of 2. And just like with any multiplication, we are able to keep these together, and the most simplified version of this would actually be to leave it like this. And as you guys know, I'm notorious for forgetting to put my equal signs in, so I'll do that now. And this is actually my final answer here. 2 root 2 is my final answer. And I know that that seems kind of weird for those of us who have never been exposed to this before, but actually you'll see, actually if you even look at some university physics textbooks, they leave answers like this all the time because it is the most simplified version of this number. Okay, so let's do another example to kind of get a better look at this. So let's go ahead and try root of 32, which this is a radical. And using that same logic that we used before, we want to break 32 down into 2 or 3 numbers that perhaps can give us a better and more simplified version. And the way to do that is by recognizing that 32 is actually built using the numbers 16 and 2. And I know that 16 is a perfect square, so that's going to be wonderful for me because I'm going to be able to split this up into root 16 times root 2. And then 16 is just going to be simplified into 4. And the root of 2 is going to stay the way it is. And this is actually going to be 4 root 2. So that's the final answer for that one. I'm going to go ahead and try one more just to give you guys a lot of different ones to kind of practice with and look at. And obviously these get more complicated, but again, as with all of our learning here, we do want to try the very simplified version first because that's going to give us the best understanding, and then we work our way towards more complex problems. So let's take a look here at where'd it go? Just give me 1 second, guys. Sorry, I put something in the wrong spot. Okay. So let's try root of 54. And I'm going to pick this one because it's going to illustrate an example about what I want to show you guys, or an example of what I want to show you guys. So I know by trial and error that 54 is divisible by 3, and so I can break this down into root 18 times 3. And another way that I can also break this down is root of 27 times 2. Now, I'm going to go ahead, and it doesn't really matter which one of these I start with because it's going to give me the same answer in the end. And that's really what's the most important thing. Obviously, you know, it's important to understand the algorithm and the steps, but whether you do it one way or the other, it doesn't really matter at all. Now, another thing I'm going to do is further break down this 18 into 9 and 2. Oh, that's not 6. Gosh, goodness. Sorry guys, my head actually really does hurt, so I apologize if I'm making little mistakes. Please feel free to call me out in the chat. I'm going to try to be cognizant of what I'm doing. But yeah, just please bear with me today if you don't mind. So another thing we can do here, 9 times 3 times 2. As you can see, like I said, it didn't really matter which one of these I chose. They're going to both be the same thing in the end. So again, we can break this down further into root 9 times root of 2 times root of 3. And again, same thing over here. Okay. So now I'm going to give you guys a second to write that down because I know that last week people were mentioning I write really fast sometimes, so I'm going to try to be more aware of that. And if you have questions about what I'm doing so far, feel free to drop a question in the chat. I'm happy to answer that for you. Okay. So now I'm going to show you guys a trick, and that's why I picked this question, because it's kind of important to be able to understand how we can go backwards and forwards with these questions. So in this case, I know that the root of 9 is actually just the number 3. So I'm going to have that perfectly set out for me. Now, I also still have the root of 2 and root of 3, and I know that if I was to square root either of these numbers, both of them would give me just crazy decimals, and they're not perfect squares, so I'm going to avoid doing that by actually regrouping these two together. Oh my gosh, I keep doing this. Great. There we go. That's a bit better. And now I will get my final answer, which is 3 root 6. And if I was to do the same thing on this side, you'd get the exact same answer. I'm just not going to bore you guys by doing it twice. But basically, what I wanted to show you in this sequence or this algorithm was this step here, or kind of going from this step to this step. Because here you can see that even though these were separated, I can bring them back together and simplify them to give me the final answer, which is 3 root 6. So now, keeping this all in mind, let us work backwards to change a mixed radical into an entire radical. And if we recall, this is what an entire radical looks like right there. And then a mixed radical, an example of a mixed radical are any of these answers that we just got. So I keep pressing the wrong button. This is a mixed radical because there's a coefficient in the front. This is a mixed radical. This is a mixed radical. So given that we were showing all of these steps to get to an entire radical, which is kind of to go from an entire radical to a mixed radical, you'd think that it wouldn't be that important to go go backwards, but actually it does often come up on tests, and it's actually just really important to understand how you can go from one to the other because it'll help you solve more complex problems. So what I'm going to do is show you guys the backwards version of this problem right here. So if we want to convert a mixed radical to an entire radical, we have to work backwards. And if we recall, how we got our mixed radical here was that we square rooted the number 9 and we got 3 as our coefficient. Well, let's keep in mind then that the coefficient number that's in front of a radical in the mixed version of a radical is actually just a square rooted number. And keeping that in mind, we can actually just work backwards. So if I'm starting with the mixed radical of 3 root 6, and I recall that this number here, the coefficient, is actually just a square rooted number from inside the original radical, then I can actually go ahead and put that back into the radical like this, squared. And then we know that we can go back to our initial question. So this is really important because you will get questions like this on tests, and just having this understanding is important. Same thing with this one. So I know that the 2 that's in the coefficient is actually a square root of something. So if I bring it back into the radical, I have to bring it back as its squared answer, which is 4. And then in this case, it's 8. And then, as you guys see, those answers are correct. And then this last one, we can go ahead and just square root that back in. And this becomes, or not square root, square it. And then that becomes this. And this becomes this. Simple as that. Okay? So that's kind of the beginning of this whole part of this unit. If anyone has questions, I'm just going to stop talking for like 5 seconds so that you can drop them in the chat. If you don't have questions, that's fine too. We'll move on to the more complex aspects of this unit so that we can just get really good marks and, you know, be all around less stressed. Okay. All right. So, having this core understanding of this, I guess, just fundamental concept, we'll say, is really, really important because at the end of the day, we're going to be adding radicals and multiplying them and dividing them. And if you don't get this stuff, that's where it gets to be much more complicated than it actually is. So if you have any questions, feel free, even if after I've moved on from a certain topic, feel free to ask them. That's totally fine. Okay, guys. So we just learned how to take a mixed radical and change it into an entire, and then vice versa. So what we're going to do now is show you just somewhat more complex versions of those before we go on to adding and subtracting, because you will see very, very intense versions of these radical questions. Sorry, it's allergy season, you guys. I apologize. So oftentimes the ones that are most complex actually have letters in them, and that's where they get a little bit crazy. But what I want you to recall is that, again, all a radical is just a bunch of numbers that can be broken down. So in this case, we also have letters, but really those letters represent numbers. And that's important to remember as well. So another way that we can break this down, and again, I'm sorry my voice is going, you guys. Like I said, I'm feeling a bit under the weather today, but we are going to keep on trekking. Thanks, that trick made it very clear to me. Thanks, I appreciate you guys commenting. Thank you, Flochi. I hope that this is helpful for you guys. And again, I know that for those of you who have done this unit, this might be a little bit of review, but I would rather review and make sure that everyone understands and work our way to the more complex parts than skim over stuff that people might have questions about, which I know is something that some teachers do, and not all. Again, I have so much respect for teachers, and I know that there are some amazing math teachers out there, but just like with every profession, there's the good and the bad. So for those of you who maybe didn't get this explained, I want to make sure that everyone has that same basis to work from. Okay, so as you guys see, I broke this up into 16 times a squared times a, and really this means a to the power of 1. And ultimately, this can be further broken down. So let's go ahead and do that. Again, some teachers don't expect you guys to do this middle step, and that's fine. If your teacher doesn't want that, that's perfectly fine. I find that this helps people, so that's why I stick to doing it. So we've got a squared and then square root of a, and they're all multiplied by each other. And so then this gets broken down. So 16 squared is, or square root of 16 is 4. The square root of a squared is a, and we don't know the square root of a because a is an unknown variable, so I'm going to leave that the way it is. So actually, our final answer to this is 4a root a. Okay, I hope that makes sense for you guys. We're going to do another example now. I'll switch the color just to be fancy. You know what? No, let's do blue. Okay, let's try this one. So we've got 4x squared y to the power of 5. Alrighty. So again, let's split this up as much as we can. So I'm going to put 4 by itself because that's a number and that's just the easiest thing to do. Then I'm going to have x squared by itself, and then y squared I'm going to break up into y to the power of 5. I'm going to break up into y squared times y. So the reason I'm doing this, and you could just leave it as y to the power of 4, it doesn't really matter. The reason that this is going to, and actually, you know what, I am going to put it as y to the power of 4 just so I don't confuse anyone. So if you're confused by how this y squared or y to the power 4 and y thing works, I highly recommend going over your exponent laws. That will help you with this unit. And yeah, it's a great thing to know in math in general. So let's break this down. So 4 squared is 2, or I keep saying it backwards. The square root of 4 is 2. The square root of x squared is x. The square root of y to the power 4 is y squared. And again, I don't know the square root of y, so I'm going to leave it like that. So our final answer here is 2xy squared times the root of y. Okay, so I'll leave that up for a couple seconds just so anyone who's copying it down can continue to copy. And hopefully this makes sense to you guys. But again, like I said in the beginning, these are just square roots. There's nothing crazy about them. It's just about recognizing which numbers are the easiest for you to use to simplify this. And this is why I'm going to go on a bit of a rant here, but this is why I'm actually very against the fact that they stopped making kids know their multiplication tables in elementary school. Like, I don't know, I think your generation probably still knows their multiplication tables to some extent, but nowadays they don't expect kids to memorize their multiplication tables, and it's really, really detrimental to their overall mathematics success. Because as you can see, having a really good grasp of your multiplication tables will help you in situations like this. And I'm sure that you've kind of intuited that on your own as well as you were doing factoring last year and all sorts of math problems that really do necessitate the knowing of your every times table. So anyways, rant over, that was it. But yeah, so these are your final answers. Wow, my square looks terrible, but you guys get the point. All right, guys, so let's go ahead and understand how the different functions of this whole situation work for us. So we're going to learn how to add and subtract these, and we're also going to learn how to multiply and divide. So adding and subtracting rational expressions is really not rational expressions, sorry, radical expressions is very much like adding and subtracting fractions, in the sense that you cannot add and subtract radicals that don't have like terms. And I'll show you what I mean. So for example, if I had root 2 and root 7, I cannot just add these two together, in the sense like I would have to actually get the decimals. I cannot group these as like terms. But if I had root 2 and 5 root 2, they have a like term, the radical 2. So this actually is the same thing as saying 1 root 2 plus 5 root 2, which really equals 6 root 2. Okay? Now I hope that makes sense for you guys. We're going to show you a bunch of examples. So if it doesn't make sense, that's totally fine. That's what we're here for, you guys. And again, there's no problem if you want to ask a question if it's something I already moved on from and you still have a question, just let me know. I'm happy to work back as well to go back and look at that stuff for you. Okay, guys, so let's try an example here. Now, you might get situations, and really this is what happens most of the time, is that you're going to get problems where you're expected to simplify the expression so that it can be added. And that's where this unit gets a little bit more complex, and it really involves you having a strong understanding of what's going on. So I'll show you another example. So if we have 3 root 7 plus 5 root 7, again, as long as the radicals are the same, the coefficients can be added, because it's the same kind of thing as saying 3x plus 5x, because we treat the radical almost as an unknown number. It's not actually, obviously you could just plug in that square root of 7 into your calculator and get some crazy decimal, but the reason that we don't do that is because, again, it makes it too convoluted and it doesn't keep the math clean. So in order to do very, very complex problems in a more simplified manner, we actually would just go ahead and add the coefficients together. And that would just be 8 root 7. Because again, it's kind of the same thing as saying 3x plus 5x. Okay? And again, it's when I say kind of the same thing, I mean don't conflate the two, but just remember that the concept and the algorithm work similarly in that sense. Okay, so let us move on to something a little bit more complex, where we actually need to apply all the stuff we've just been learning. So I'm just going to erase this. Actually, you know what? No, we will just leave that in case we need to refer back to it. But let's take a look at something like 7 root 18 plus 3 root 20 plus root 50 plus root 80. Okay, so for each of these, I'm going to use different colors just so that we can kind of keep things streamlined. But what we're going to do now is break these down and simplify them as much as humanly possible. And let us get some colors up in here. So let's start with this one. So 7 root 18, I know, can be broken down further. And I'm going to leave the 7 where it is because typically that's what you want to do. You want to leave it as its mixed form as much as you can, unless bringing it back into the entire radical ends up helping you simplify it more. So now we're going to go ahead and try this next one, which again I said we would use different colors, so I should stick to my promises. So for those of you that live in Simcoe County, I'm not trying to do Innisdale's colors, it just happened. Okay, so 20 can be broken down further into 4 and 5, and we know that 4 is a perfect square, and again, we're always aiming for those perfect squares. Let's do purple to bring St. Pete's in, make everyone feeling a little bit more fancy. So this can be broken down into 25 and 2. And actually, I wrote the question wrong. This is supposed to be a subtraction at that point. So I'll fix that real quick. That's a subtract sign, a minus. Okay, and last but not least, which I should change the color again anyways, let's do pink. So 80 can be broken down into 16 and 5. Okay, so this is plus, this is minus, this is plus. Okay, guys. So now that we've done this section and this portion of the question, what we still have to do is still really simplify these questions. And what is going to happen is, just like we were doing before, we're going to go ahead and square root things if they need to be square rooted. So this becomes 7 times root 9 times root 2. Should just keep this open, but it just blocks the thing. So 4. I know that's not the right color of orange, but just bear with me, guys. Then this becomes root 25 times root 2. And last but not least, this becomes root 16 times root 5. Okay, great. Now let's go ahead and break them down even further. So here we're going to get 7 times 3 times root 2. Here we're going to get 3 times 2 times root 5. I'm back on the proper orange color there. Here we're going to get 5, because the square root of 25 is 5, times root 2. And last but not least, we're going to get 4 times root 5. Okay, so we've got this whole situation now. I'm going to go back to using one color just so that we can illustrate something. So 7 times 3, that's going to be 21 root 2. This one is going to become 6 root 5. This is going to be 5 root 2, as you can see that already is like that. And here we've got 4 root 5. So remember what I was saying earlier about like terms. The radical describes the like term. Therefore, all we need to do is determine which are like terms. Well, here I've got 6 root 5 and 4 root 5, and I move them with their sign. Okay? So I'm going to put that first here. 6 root 5 plus 4 root 5. And then on the other hand, I've got 21 root 2 and negative 5 root 2. So 21 root 2 is assumed to be positive because there's no sign in front of it. So we've got 21 root 2 minus 5 root 2. Great. Wonderful. Let's keep on going. Okay, now all we need to do is add the coefficients. I'm going to do this all in one pen color here. So 6 plus 4 is going to be 10 root 5. Wonderful. Just hold on one second. Oh, okay. I wrote the original question down wrong, but we've been following the steps that we wrote correctly, so it doesn't really matter. So everything is fine. Everything we've done so far makes sense. And then we've got 21 minus 5, which is going to be positive 16 root 2. So as you can see, the radicand, the radical basically, stays the same. This is our final answer. It does not get more simplified than this, folks. We are out here living the dream, okay? Wonderful. So, I'm going to leave that up for a second. If anyone has questions about this, do not hesitate to drop the questions in the comments/chat, and I'm happy to answer them for you. Okay. So if you guys are unclear on everything that we just did, I can do another example. So if you want me to do another example, just leave me a question, a comment in the chat. But what I do want us to move on to are multiplying and dividing radicals, as well as rationalizing the denominator. So I don't want us to run out of time, and as such, if everyone is okay with what we've done so far, then I'm just going to hop on to the next topic. But if you would like me to continue on this adding and subtracting topic, I'm happy to go over another question for you, okay? Just let me know. I'll leave like a 5-second delay here. Alrighty, guys. So let us move on to multiplying and dividing radicals. We're going to start with multiplying first, and then we will move on to dividing. But I'll just start a new page here. Alrighty. So just as before, which let me actually use the pen function, that would be helpful. Let's use a darker color. Ooh, you know what? No, I never use this purple color and I do love it. So let's go ahead and do that. Alrighty. let's take a look here, guys. So let's say, for example, I have the expression 7 root 6 times 5 root 2. So I want to teach you guys the rule of multiplying radicals, and that is that when you have two radicals multiplied by each other, imagine with fractions how you have numerators times numerators and denominators times denominators. Well, here you have coefficients times coefficients and radical times radical. And the way that's going to look is like this. You've got 7 times 5, and you've got inside the root 6 times 2. Wonderful. So let's get those answers. We've got 35 on this part, and over here we've got numero 12. So let me fix that, make it look less like a serial killer wrote it. Okay, great. Now, kind of everything we've learned so far tells us that this obviously cannot be the final answer because it's not simplified enough. The number 12, which is inside the radical, can be simplified further. And that's really the indicator that you should be looking for to know whether or not your answer is done or not. If the number in the radical can be further made like smaller and simplified more, that's how you know you should keep going. And once you've reached the most simplified form and it cannot be divided further, then you stop. All right, so let's go ahead and do that. So we've got, it's quite a large number as our coefficient, 35, and we break this down into 4 and 3 because I know that 12 has this perfect split of 4 and 3 because 4 is a perfect square. And all that's going to look like is like this. If you really wanted to be fancy, separate them. Okay, great. Now we know that 4 and the square root of 4, is 2. So this is actually going to become 35 times 2 times the root of 3. And our final answer for this question is actually 70 root 3. So again, our goal is to get the number inside the radical as small as humanly possible. And sometimes that means that the coefficient is actually going to be quite large, and that's fine. It really doesn't matter if it is or isn't. Wonderful. Okay. Now I'll show you where this becomes complicated. And just like with all math, it becomes complicated when we have to have factors. Okay, so let's write it out. We've got 3 plus root 3 times 4 plus 3 root 3. And when I first was learning this in high school, I just hated these kind of questions because I just found that they complicated things and it's just annoying. So if you are a person like me who, upon seeing this the first time, is not a fan, just know that as you practice the more, it does get a lot easier. And I know that I say that from a place of privilege because obviously I've practiced this many times as a tutor, teaching it to other people, but you can achieve that level of practice as well. And it really just comes down to putting pen to paper and trying these skills out, okay? I don't want to sound like a broken record, but honestly, guys, it really does come down to that. Like, math is all about practice. Nobody is just born, I mean, okay, look, there are some people that are born math geniuses, obviously, but most people are not born just being great at things. You have to work at it, and math is one of those things. But that doesn't mean that you can't become great at it. Okay, so using our saber-tooth method, as one of my old students used to say, we're going to do that multiplication. So obviously 3 times 4 is going to be 12. And then 3 times 3 root 3, well, 3 is a number, and times 3 root 3, those two numbers are going to multiply. So it's actually going to become 9 root 3. The root stays unchanged. So let's do this now. We've got root 3 times 4, so this becomes plus 4 root 3. Because 4 root 3 is the same thing as saying 4 times 3, in the same way that 4 times x is the same thing as saying 4x. Okay? Sorry, I don't mean to freak anyone out. I just got really riled up about that real quick. All right, so, and then last but not least, we've got root 3 times 3 root 3. And this is where this becomes interesting. So, and this is actually the part where a lot of people that I've tutored have become confused by these types of questions. So I want to address this really carefully. So again, we're taking root 3 and multiplying it by 3 root 3. So how does that look? The 3 in the front stays the same. And then we've got root 3 times root 3. Okay? Because remember, from here, we know that the inside of the radicals actually multiply by each other. Okay, so let's go ahead and figure this out and how it works. I'm going to change the color because it's starting to get... This is very bright color. Okay, so 12 stays the same, obviously. All this other stuff stays the same for now. We're going to deal with that later. And here, I can consolidate this like this. Or, it's the same thing as saying square root of 9, because 3 times 3 is 9. And then, realistically, in my next step, I should show that because that's a perfect square, and I know that the square root of 9 is 3, this now becomes 3 times 3. The root of anything times the root of any, like the same thing, is always the thing inside of the radicand. So it could literally be like root of monkeys, and I always use monkeys as an example. I just like monkeys for some reason. But the root of monkeys times the root of monkeys is monkeys. And for those of you who like the reason why things happen, to know why certain things happen, think of it like this. And if you haven't done this part of this unit yet, I'm sorry. I'm just going to do like a quick exponent law class here. But this is the same thing as saying x to the power of a half, because the square root is equal to x to the power, like root x is equal to x to the power of a half. It's the same thing. They mean the same thing. Oh. So the reason why this becomes just the thing inside of it is like this. Okay, so if I have x to the power of a half times x to the power of a half, our exponent laws tell us that when you multiply two things with the same base, you actually add their exponents. So this is realistically x to the power of a half plus a half, which becomes x to the power of 2 over 2, which is x to the power of 1, which therefore means that we've now basically canceled out our square roots. Okay? This is something that occurred to me literally as an adult, and I wish that it had occurred to me as a teenager, so that's why I always bring this up when I teach this, because I find that a lot of people get confused as to why the square root goes away, and I'm the kind of person that likes to know why things happen in math. I find that it just helps me understand. So if there's anyone else out there who thinks that way, I hope that that helped you. Okay, so we're going to move some of this stuff just so that we don't confuse anyone. And I actually think we will do an exponent laws class, because I know that exponents are kind of part of the grade 11 curriculum. I've been leaving them till last because I've been trying to focus on pieces of the grade 11 curriculum that are kind of what we'll call endemic to the grade 11 curriculum, which means that they only are like this is the first year you've kind of been exposed to them, because those are typically the units that people struggle with the most. But as we get closer and closer to the end of the semester, I am going to address areas that are also more common math problems, so that everyone who might be struggling in those areas can also get the help that they need. Okay, enough of my blabbering. Let's get back to the problem here. So I'm just going to quickly simplify this last part, because again, BEDMAS. And now we're just going to collect like terms. So this here has like terms, and then these are like terms, 12 and 9. So I'm going to rewrite this as 9 plus 4 root 3, because again, the coefficients get added, and 12 plus 9. So here we've got 13 root 3. And here we've got 21. And if you have a teacher that wants you to simplify this further, aka have it as a decimal, that's great. This is actually the most mathematically correct answer. Putting it into a decimal again would be incorrect as far as mathematicians are concerned. But again, I know that in high school it really depends on your teacher and it depends on their level of exposure to higher level math. So some teachers who have not been exposed to like master's level and PhD level math courses might actually expect you to give a decimal answer, and that's fine. You can totally do that. You would just plug in root 3 times 13 plus 21, and you'd get like 43.52-ish. But again, for our purposes, we're going to leave it like this because this is the most correct way to do it. All right, my friends. So hopefully that made sense. We're going to do one more example of this type, and then we're going to go ahead and take a look at the division, because oh my god, it is 4:50 almost. Wow, guys, time flies when you're having fun. I'm having fun. I don't know about you guys. But we will try to get as much done as we can. If we don't get to division today, that's okay too. We've got next week, because as I've said before, we are going to continue doing free math help as long as the semester goes on, or if you guys go back to school, obviously we're going to have to stop doing it. But yeah, so there we go. So 5. Sorry, I'm just rewriting it because it got messy real quick. Okay, so this example has pretty much more radicals in it than the first one did. The first one had more just numbers on their own. That's okay, because again, we know our rules, and as long as we know our rules, we know everything that we need to do. All right, guys. So again, follow our FOIL rule. Root 5 times root 5. Remember what we were saying earlier. Root of monkeys times root of monkeys equals monkeys. So in this case, that equals 5, because it's the same thing inside both of the roots, and you're multiplying it by itself. Here we've got root 5 plus 3 root 2. So this is going to become 3 5 or root 5 2. You guys see what I'm writing. Sorry, sometimes I mix up the words. And then here we've got root 2 times root 5, which is just going to look like this. And last but not least, we've got root 2 times 3 root 2. But again, we know that square root times a square root is equal to the number. So that's actually just going to become, well, technically it'll become root 4. But you'll see in a second how that's just going to become 2. So let's simplify this. Okay. And I'm just going to further simplify this. So you see here that we got 3 root 2. Sorry, 3 times 2. I'm just going to turn that into 6. So I don't have to rewrite the same thing over and over. But if anyone's confused as to how I got that, just let me know. Okay. And last but not least, this does not have a 3 in front of it. That's what I was like looking at this. I'm like, why did I write this so weird? And then I see what I did. Okay. Last but not least, we're going to bring together like terms. So 3 root 10 plus root 10 is the same thing as saying 3 root 10 plus 1 root 10. So that's going to become 4 root 10. And then 5 plus 6 is 11. And that's our final answer, you guys. Oh, this box looks, I ruined it in the end. Damn it. Whatever. You guys saw that it was on its way to being a great box. One of my favorite math teachers from high school, he used to come into class every day. Not every day, but a lot of the time. He'd come into class and he'd tell us, did you know that if you could draw a perfect circle, you're considered to be clinically insane? And then he would proceed to draw a perfect circle on the board, like a huge perfect circle. And then he'd turn around and just look at us and laugh and kind of like give a maniacal laugh. Anyways, he's a wonderful... Okay, thanks for doing another one, but it is making sense. Okay, awesome. Anyways, that teacher was awesome. I hope he is well. And yeah. So, okay. Do we have time? Yes, we are going to quickly learn about the division. And then you guys can go back to having a grand old time. But as I always say, if you have questions that your teacher has given you, even if they have nothing to do with the lesson that we're teaching, we're happy to address them. And if they're the kind of questions like a graphing question or something that you can't submit in the YouTube chat, you can actually email them to us here at admin@scholarlyelite.com. That's that is the address, the email address for our tutoring company, and the team and I will put them on the list to be addressed next week. Okay, so let's take a look at the division of radicals, which is also a really, really important part of this unit. So when we're dividing radicals, the rule is kind of similar to what we were just learning about multiplying radicals. So if we had, for example, and I'm going to use letters here quickly. So if I had a root x divided by b root y, another way that I can write this is a divided by b, so the coefficient number on the numerator is divided by the denominator number, and then you have x divided by y. Simple as that. So let's say, for example, we had 16 root 55 divided by 4 root 11. Another way that we can write that is 16 divided by 4 and 55 divided by 11. And so that's going to equal 4 root 5. And that cannot be simplified any further, so we're just going to leave it like that. All right. So I'm going to do another example, and I'm also going to show you guys kind of a trick that is important to understand. But one thing I do want to mention is that, where is it? That again, like if you had a number in the radical that could have been more simplified, then you don't leave this as the final answer. In this case, it is the final answer, obviously. Wow. In this case, it is the final answer. But in situations where the radical can be further simplified, it would not be the final answer, and you would have to continue to simplify it, even though you've already done the division. Okay, let's try another example here. And I'm just going to, you know what, I'll leave that and I'll just use another pen color. We'll do it on the side here. Ba-da-ba. Okay, so let's say I have 6 root 15 over 3 root 3. Then obviously this is going to become 6 divided by 3, which is 2, and 15 divided by 3, which is 5. Okay, that was a kind of simple one. One thing I do want to show you guys is that if you have a square root of a whole fraction, so let's say, for example, like 20 over, I don't know, 10. It's the same thing as saying root of 20 over root of 10. Okay? So even though you've square rooted both the numerator and the denominator, kind of as a whole thing in this top part, you have to be cognizant of the fact that you can break it up, and then these can be further broken down. So for example, and again, I just kind of made this up so it might not come out as a perfect example in the end, but I just wanted to illustrate this to you guys, that this can be further broken down into 4 times 5. This can be broken down into pretty much nothing. So we're just going to leave that. But this final answer would be this. Now, is that actually the final answer we would leave? No, and that leads me into our next topic, which is rationalizing the denominator of a radical expression. So basically what that means is that we never want to leave a radical number in the denominator of an expression. And the reasoning behind this is actually quite complex. So I'm not going to get into that. I don't want to confuse people. But just know that kind of your final answer for any of these kind of questions is never going to be a number where you have a fraction with a denominator that is a radical. So what that means is that we have to rationalize the denominator. I'm going to show you guys with a simpler, no, actually I'll show you with this example. It's not a big deal. So to rationalize this denominator, what we have to do is multiply both the top and the bottom by the radical that's in the bottom. So I'll show you why that matters and why we do that. So I'm just going to put a little note here. This is called rationalize. I keep saying it, but it's really important that you guys remember this terminology, rationalizing the denominator. Please, please, please remember this. This is actually a very important skill for all of the rest of math. I probably won't have time to show you more examples that are more complex today, but next week I do want us to address this again in a more higher level way, just because it is something that you'll have to know how to do for grade 11, for grade 12, calculus, and even beyond. So just super important. So remember how earlier we were talking about how any radical times itself is what I'm trying to say, is going to actually equal the number that's on the inside. Well, that's really what's happening here, because root of 10 times root of 10 is going to equal 10. So let's do our normal fraction multiplication, which is the numerators times the numerators and the denominators times the denominators. And then we're going to be left with, so this is going to be 2 times root 50 over 10. And that can be reduced, but we're not going to do that just yet. What I am going to do first is continue to simplify this numerator. So the 50 can be broken down into 25 and 2. Again, the 10 stays the way it is for now. And this becomes 2 times root 25 times root 2 over 10, all over 10. And then this becomes 2 times 5, because the root of 25 is 5, times root 2 over 10. And then this becomes 10 times root 2 divided by 10, which logically is going to be canceling out here. So this just becomes the root of 2. Okay, you guys? So that's pretty much our lesson for today, because if we were to continue on with the rationalizing stuff, it does get quite a bit more complex, and I don't want to confuse anyone in the next 2 minutes. So I'm going to let you guys go about 2 minutes early today. Unless anyone has any questions, which if you do, feel free to leave them in the chat, or again, email them to us at admin@scholarlyelite.com. You're more than welcome to, and we can address those next week. But next week we will come back to this topic just quickly so that we can basically, actually I'm just making a note of that right now so that next week we can. But basically we'll come back to this topic so that everyone can have a better understanding of how to do these types of problems when they become more complex. Okay. Anyways, guys, have an awesome week. I'm wishing you all the best. And if you, like I said, if you have questions that we didn't get a chance to get to today, send us a message at our email, and we can definitely help you with that. Okay? So have an awesome day, you guys, and talk to you soon. Bye. Okay, so if you are just tuning in for the grade 12 chat for the live stream, I want to say welcome. I hope you guys are having an awesome day so far. If this is your first live stream with us, welcome, and I hope that you have some questions for us if you do, and if you don't, we always do a lesson, so feel free to stick around and watch the lesson. I'm just going to make sure that I have all the correct materials to teach you guys this lesson, and then we can be on our merry way. So give me one quick second, but in the meantime, if you have questions, just feel free to drop them in the chat, and I'm happy to answer them. Okay. So guys, today what we are talking about is the, let me just flip this slightly. Good. Today what we're going to be talking about are the wonderful trigonometric graphs. And I was just telling the grade 11s I didn't do trig graphs with them just because I have a migraine-ish. I'm starting to get a migraine anyway. And I just don't think I could have handled doing it 2 hours in a row. But we are going to do the grade 12 class 1 because I actually find the Radians version a little bit easier, and obviously you guys have been exposed to trig functions before, so it's a little bit better for understanding. Alrighty, so let me just put some lines here. Oh my gosh, my lining situation is just bad. Just bad news bears. Anyways, okay. Try that again. Do it properly this time. Yay-ish. Proper-ish. Okay, guys. So, these past couple weeks we've been talking about trigonometry, and obviously that has been just like the most fun of your lives ever. I'm sure you have been thoroughly entertained, but obviously we know that trigonometry is just a never-ending situation. There is more than one trigonometry unit in the grade 12 advanced functions curriculum. Most importantly to note, the grade 12 advanced functions curriculum has a strong focus on trigonometric graphing, which as you probably remember from grade 11, is super wonderful and awesome and fun. So without further ado, we're going to get into that. But before we do, I thought I'd leave like a 5-second pause here to see if anyone had any questions about anything else that you might want us to address. But if you don't, then we can just go on to trig graphing. Okay. Also, guys, just a heads up that depending on how bad my migraine gets, we might wrap this up early today, and I'm really sorry about that. Just please bear with me, because I do want us to get as much done as humanly possible, but we might have to call it a day if I get to a point where I cannot even look at the screen anymore. So, first things first that I want to talk about are really just kind of like what are the graphing, what are the trigonometric functions, and what do their basic versions mean to us. So we know that we've got y equals sine of theta, and we've also got y equals cos of theta. And I'm going to put that actually in a different color just for fanciness purposes. Actually, I should put them both in different colors that are not blue for the sake of clarity. So y equals sine of theta, and this one can be y equals cos of theta. Yay! Wonderful. Just wonderful. All right, guys, so one thing that's really important to remember, I'm going to use a new page here just quickly to express this, is that we've got, where did it go? In our two special triangles, there we go. Oh, that's creepy. Look, it looks like one triangle is like the ghost of this triangle's body and it's leaving its body. Anyways, sorry guys, that's how my brain thinks. So, God help us all. Oh, that's creepy again. How many times did I do this? Just the two? Wonderful. Yay! So we've got our two standard triangles, and if we recall what I've been saying to an annoying degree these past couple weeks, is that if you memorize your two standard triangles, you have memorized the entire unit circle, and you don't need to worry about nothing ever again. Okay? You don't need to use the New York Italian accent like I just did, but, you know, doesn't really matter. You can if you want, because it's a respectful and wonderful accent. So this is going to be pi by 4, which can also be described as 45 degrees if you fancy like that. Then we've got pi by 4 here as well. And we know that this is root of 2, this is uno, that's uno as well. All right, and then on this side, we've got 2. Oh, sorry, let me put the angles in first. So then we've got pi by 6, also known as 30 degrees, and pi by 3, and this is root 3, this is 1. All right, so like I've said, you should have these standard triangles literally seared into the back of your mind. And I don't mean that. I mean that, I don't mean that literally. Like, don't actually sear them into the back of your minds, but you get what I mean, that you should have them memorized. Standard triangles in radians. Okay. Wonderful. Well, remember that when we know these standard triangles, we know every value on the unit circle, and realistically what we're doing when we're graphing the values of sine and cos of theta is literally just asking what the different values of cos and sine are throughout the unit circle. So remember that cos and sine can be indicated as x and y. They follow the same rules of x and y on the Cartesian plane, and that if this is 1, this is 1 on the x, this is 1 on the y, right? And we're just kind of going around the unit circle. Pretend that my circle was better, but you guys get what I mean. You're just looking at the different angles. So you've got like 30, 45, 60, 90, so on and so forth. And that's really what we're graphing when we say that we're graphing a trigonometric function. So if we come back to this one, and I'm just going to go ahead and put some numbers on here. So we've got, this is going to be, I'm going to make this into 1. I'm going to make this into -1. Okay. So, if you recall from last year, we know that every periodic function has a period, which means that it has a certain amount of time that it elapses over before it repeats itself. If you know the unit circle, you know the period of sine is 2 pi, because that's what it gets to eventually, right? And obviously that can change with transformations, the same way that the period of sine was 2 pi, not 2 pi, 360 degrees before. Sine and cos both have the same period when they are not transformed. Okay, so let's go ahead and draw that out. Again, if anyone has any questions, just feel free to drop them in the chat. We're about to get rolling here. Just give me 1 second to make sure I have the right version. So let's break this up like this. If I've got, this is going to be pi by 2, aka 90 degrees. This is going to be pi. Actually, should we make those further? Yes, because people might get confused. Okay, so let's do this. We've got Okay, same thing here. 1, 2, 3, 4, 1, 2, 3, 4. This one doesn't work exactly for this one, but that's okay. Okay, so let's label these. We've got pi by 2, we've got pi, we've got 3 pi by 2, and we've got 2 pi. So let's go ahead and see what this means. Again, it would be helpful for you to have a unit circle. Just give me 1 second. I'll actually pull one up to make this easier for you guys. Let me just put this into my desktop. Documents. No memento, my friends. Okay, let's pull this in here and drag and drop the file that we need. Okay, so while that's converting, apparently, I don't know what the heck it needs to convert, but anyways, so let's take a look at our unit circle here in conjunction with what we're about to do. So if you recall that on our unit circle, the x values are cos and the y values are sine. So this is a cos and this is a sine. This is a cos, this is a sine, this is a cos, this is a sine. It's actually going to help us write and figure out where we're drawing stuff on here. So we know that sine starts at 0 right here because we're on the x-axis on the unit circle. So sine in its truest form starts at 0, which I should be using a purple pen. My bad, my bad. We got it. So there we go. Sine starts at 0. What's our next value of sine? Let's keep going. Well, our next value of sine at pi by 6 is 1/2. But I'm not going to show that part yet. What I am going to show are these main indicators that we've got here. So pi by 2, which is right here, sine is 1. So I'm going to go ahead and do that right there. And at pi, which is over here, it comes back to 0. At 3 pi by 2, it's -1. And at 2 pi, it's 0 again. And actually, that's really all the information I need to know for this in order to be able to connect the dots. I'm going to try to do this as smoothly as humanly possible, but sometimes when I talk about it, it gets more messed up. Okay. So this from here to here is one period of the pi function. Okay? Now the pi function in reality also goes on the negatives as well. But right now we're just going to focus on showing this, and then we're going to make it more complex so that nobody gets confused, okay? So I'm going to erase that last bit that I drew there. Now we're going to do the cos function following the same rules. If I could find my cursor. Okay, there we go. There we go. Okay, so y equals cos of theta. So again, the changing variable here, the x value on the plane that we're looking at is theta. Y is the answer. So if my theta is 0, my cos is actually 1. If we look here, see? Cos is 1. So I can go ahead and plug that in. If my theta is pi by 2, my cos, which is the x value here, is actually 0. And let's go ahead and take a look at pi. So at pi, my cos is -1. And at 3 pi by 2, my cos is 0 again. And at 2 pi, my cos is 1. So again, this is one period of the cosine function. one way to tell that you've accomplished a full period of something is that it actually goes back to where it began. So in this case, it began at 1 and it went back to 1 at 2 pi. So that's not the most streamlined line, but you guys kind of see what I'm saying. And again, this would continue on over here, as with the pi, as with the sine function. They both keep going, right? And this follows the same pattern over and over and over again. And that's kind of the point, and that's why these are called periodic functions, because periodically they repeat themselves. Okay. And it's interesting because this is a non sequitur kind of, but it's interesting because sometimes math helps us understand words in English and what they really mean. And I think the word periodically is one of those words where having an understanding of periodic functions actually helps you understand what the word periodically means in English. Okay, so I'm going to leave that like that for a second. If anyone has any questions, let me know. And if not, we'll just keep on trucking. And before we go on to transformations, I do want to discuss a couple of things about this stuff. Okay. For those of you who are new to trigonometric graphing, if you have the app Desmos, it's actually a really good way to check your answers for the stuff we're going to learn next. If you don't have Desmos, highly recommend downloading it. I mean, it's not foolproof. It is kind of annoying in some ways. That said, considering it's a free app, it's pretty much a gold mine of information. I highly recommend, if you're not familiar with how to use Desmos, try watching some YouTube videos on how to fix the X and Y's in Desmos. It'll actually make your life a lot easier. Make sure that if you are graphing in Radians in Desmos, that you have the Radians setting on, because it can make a big difference. But yeah, so alrighty, moving on. A couple things we need to discuss about this stuff. So for y equals cos of theta, we need to determine what is the domain and range. So the domain and range of both cosine theta and sine of theta are, so for domain, we'll do this. So domain is x is the element of all reals, and it can be from negative infinity to positive infinity. I know you guys can't really see that, but I'm just trying to say it out loud so that everyone can get what I'm saying. And then the range is obviously 1 to negative 1, or negative 1 to 1, because we start with the negative number, and that would be y is the element of all reals. Negative 1 is greater than or equal to y less than or equal to 1. Okay, I know that looks kind of cringy on the writing side, but that's that. Alrighty. So if anyone has any questions about that, let me know. I'm happy to answer them. But if not, we're going to move on to the more complex part of this unit, which is all about transforming sine and cosine graphs. So as I told my grade 10s last week, understanding the transformations of graphs is literally like the holy grail of math. Those of you who have a great understanding of how transformations work really have it much easier. And I can't imagine that it just automatically clicked for anybody, because it's not how it works. You have to try them. You have to have a little bit of practice in order to get to the point where you understand them fully. But just before I go, I want to make sure that these are indicated properly. Okay. Great, guys. So let's take a look at the transformation of graphs. So let's go here. So just like with any transformation of graphs function, we often start off like this. We have y equals a, and then usually when we used to have like quadratic functions, it would look something like b x minus 2, not 2, I'm trying to put a letter there, squared plus c. Because the squared was there because this was a quadratic function, and in quadratic functions, they have to have a squared. Now, when we move on to using this same type of formula for the trigonometric functions, what we actually transform this into is y equals a, and then basically from there, we put sine k x plus d, or minus d. It doesn't, we'll put minus. The technical way to write it is minus x minus d plus c. So how can we break this down? This information is super important, you guys. So please, if you haven't learned this yet, and if your teacher hasn't taught this to you guys yet, it might be coming. Obviously, you've probably been exposed to this on some level before with the degrees version of it, but it is important to understand how this all comes together. So please, if you are new to this, just write everything down. Okay, so keeping all of this in mind, a couple things we want to note. So the A, in this case, this is the amplitude. This also tells us the vertical stretch of this function. That's an A. There we go. Stretch. And I'm going to show you guys, hopefully we'll have time today. If not, we'll do it next week. But basically this can be solved for. If you've been given a graph and asked to find the equation of the graph, you can actually solve for this, as you can with any of these. Okay, obviously sine is just sine, that's whatever. This tells us something very important. This actually tells us what the period is going to be, but not directly. Not directly. We actually are going to use that information to solve for the period. Okay? So, very important. This is also another way of saying the horizontal stretch. And actually you can solve for the period by using this formula. Period equals 2 pi over k. But we'll look at that a little bit further. Noise. This part is the phase shift, as the fancy ones call it. I'm just going to erase this so that no one gets confused. This part is the phase shift, and this basically tells us whether something moved left or right. And this part is the vertical shift. So a couple of key things I need you guys to write down. Gonna do another pen color here. So there are some ways that you can solve for all of these things. So if we look back here at this, we can actually solve everything. Now, obviously here we just had y equals sine theta, y equals cos theta. But that's the same thing as saying y plus y equals 1 as a plus 0 as c. I'm going to show you how we solve for that. But just keep in mind that both of these functions go from 1 to negative 1 in their original format, right? So one thing to remember is that here we've got a maximum, because that's the highest, that it goes on the y-axis, and then a minimum. So keep that in mind as we do this. So the A can be determined by going maximum minus minimum divided by 2. And if we look at our standard y equals sine of theta function, the maximum was 1 and the minimum was negative 1. So then this actually becomes the following. And then we get 2 divided by 2, which is 1. Which makes sense because this technically is 1 sine theta. So I'm going to erase that real quick. So that's a formula that you guys should remember. And again, I know that this is a bit of a refresher from grade 11, but for anyone who might have been confused in grade 11, I want to make sure that we're covering all of our bases here. Then we've got C, and C is max plus min divided by 2. And I'm going to show you why that makes sense for the y equals sine theta function. because what really happens here is we get 1 plus -1 divided by 2, which is equal to 0. And clearly the function has not been moved up or down, so it actually having a plus 0 makes sense. Wonderful. So that's another function, that's another equation that you have to keep in mind. And like I said over here, this equation, the period equals 2 pi over k. But sometimes you'll be given a graph and asked to create the, the equation of the function. And so you might have to work backwards. So you might actually have the period because you can determine it based on like when it repeats itself, but you don't have the k value. So to work backwards, we're going to rearrange that really quickly. So if we've got period equals 2 pi over k, then by rearranging that, it becomes k times period equals 2 pi, and then k equals 2 pi divided the period. So that's actually another valuable thing. That's a pi value. So those are some important equations that I want you guys to remember. Another thing that I am going to make note of is be really aware that you cannot have a k value if you haven't fully factored out the k from this stuff. So let's say, for example, you have like y equals 3 sine 4x minus 12. Just, this is arbitrary, remember, haven't done anything yet. Plus 10, okay? I have to factor this 4 out of this first in order for it to be the k value. So I'll show you what I mean. Sorry, plus 10. And then now I can attribute that to being my k value. Okay? So just be very, very aware of that, and always, always, always ask yourself, did I factor it out? Because that's where people lose marks every time. And it's very frustrating later on when you realize that you might have lost a mark to get this answer. I'll show you guys another example of that. So let's say, for example, we have the question. I'm just going to move this up a bit, you guys. I know if you want me to go back and show it again, just let me know. Let's do another pen color. Let's say, for example, you were given the question y equals 3 over 4 cos 2x plus 2 pi over 3. And they asked you, find the amplitude, period, and phase shift of this function, right? Well, let's go ahead and do that. So the amplitude, obviously, is the a value. So again, if we were to line this up with our knowledge of what the standard equation is, we have y equals a cos k x minus d plus c. So in this case, this is a, and we have not yet factored out enough stuff to get our k value, but that's okay, we're going to do that. So amplitude is equal to 3/4, but that's our absolute value of the amplitude. But what I need to do now, because obviously that's a quick part of this question, we still need to figure out the period and the phase shift. But in order to do that, we can't leave it the way it is. It has to be factored further. So it's going to become y equals 3 over 4 cos. And then I'm going to put my square bracket in because that's when things get fancy. And I'm going to factor the number 2 out of this. So for those of you who might not be familiar with how to do that, again, you're just dividing 2 out of both this and this. And if you need to do that on the side, go ahead. So 2x divided by 2 leaves us with x. Okay, but I'm going to put that 2 in the front here, and I have x left by itself. And then what about 2 pi over 3 divided by 2? Well, that's the same thing as saying 2 pi over 3 times 1 over 2, because we're just flipping this fraction. And that leaves us with these canceling, and we get pi over 3. So this becomes plus pi over 3. Okay, so now it's important that we understand how we're going to get the rest of this answer. So remember, we want our amplitude, and we knew that that was going to be 3 over 4. And if we've got our k value, we can solve for the period. So if the period is equal to 2 pi over k, well then that means it's, in this case, 2 pi over 2. And that's just equal to pi. So this is part A of the answer. This is part B of the answer. Like this part is the answer. The pi is the answer. Which means that this actually, this function has been compressed, obviously, because usually the value of the period is 2 pi, and this is now happening much faster. And then last but not least, the phase shift is the opposite sign of what we've got there. So in this case, the phase shift is negative pi by 3. If anyone is confused by what I'm talking about, just feel free to leave a question, and I'm happy to do that. But really, this means that it's shifted left. Okay? Because basically when the original equation has a positive here, that means it shifts to the negative, and when it has a negative, it shifts to the positive. Okay. So let's go about graphing this situation that we just looked at. Okay. So in order to graph this, sorry guys, I just need to fix my glasses quickly. And I don't know how you guys, like, I use these headphones that are for gamers. I don't know how you gamers wear these all the time. They're really, really painful, especially for people with glasses. They like squish your glasses into your head. If anyone has any suggestions, please feel free to let me know, because I would love to not have that happen anymore. But that's beyond the point. So one period of this cosine curve begins at negative pi over 3, and it would end at negative pi over 3 plus pi, because obviously that's the situation. So that's one way to actually look at this, and we're going to kind of go about showing you how to do this on the graph. So I'm going to just move this stuff up. So let's bring a little graph paper onto here. See what kind of graph paper we got. No, not a fan of this one. Expand. Okay, we're gonna have to do it on this other page. No problem. We can do that. It's doable. It's just annoying, but we got it. Let's just double check one thing here. And this graph paper provided by math/aids.com. God bless them. They're a really great website. I don't know if they do high school stuff, but they must, because this was on there. Okay, back to square uno. Let's put a graph situation on here. So there we go, and there we go. Great. Okay, one thing that no one ever teaches you in any classes is that knowing the phase shift and knowing the period kind of gives you such a huge advantage, because you can actually just solve for stuff so much easier. So if we recall for the equation, let me change the pen size back to, oh, I did. Okay, great. Cool. first we need to put these lines in like this. This is y. It's x. Always label your graphs, guys, even as you get into the higher grades. It's super important. And make sure that they indicate that it goes on forever, which I just did. So remember that our answer here for that question was y equals 3 over 4 cos 2, and then this is x minus negative pi by 3. Okay. So remember that our amplitude was 3 over 4, which means that since there's no phase shift here, since there's no vertical shift here, we know that it's going to have to go up to 3 over 4. So what I'm just going to do is, this is 1 over 4, 2 over 4, 3 over 4, 4 over 4. So this can be 1, and this can be 3 over 4. And then same thing here. That's negative 1, and that's negative 3 over 4. Okay, guys, so basically the amplitude is just the distance from the middle line to the top. It's not the whole distance. That's why it was divided by 2. So again, amplitude 3 over 4. The period is pi, I believe. Yeah. And the phase shift was negative pi by 3. Great. So one thing, again, like I said, that no one ever teaches you that's actually really, really helpful to know is first how to determine what your interval is and how we can graph that. So I like to start at the phase shift and then just add the period. So if the phase shift starts at negative pi by 3, I'm just going to split this up like this. So I'm just going to move this like, this can be pi by 6, this can be pi by 3, this can be, sorry guys, I'm just trying to make sure that everything looks right. And again, as I'm doing this, and if you guys have questions about what I'm doing, just feel free to let me know. Okay. Wonderful. So, like I said, I like to start at the phase shift. So if my phase shift is negative pi by 3, that's where I'm going to start. So remember, though, that you have to put in values that make sense. So this is going to be negative pi by 6. It's going to be negative pi by 3 because, again, pi by 6 is smaller, obviously. Not smaller, but like pi by 6 is 30 and pi by 3 is 60. So keep that in mind. So I know that my cos function starts at the very top, so that's where I'm going to start it. Like starts at the top of the amplitude is what I'm trying to say. And then we're going to go from there. But what's important to also remember is that the thing that we're trying to show happens over one period. So an easy way to determine how to show it is literally just to say, where's the phase shift? So negative pi by 3 plus the period, which is going to be simplified further, but comes together at 2 pi by 3. And you guys can, like, obviously, if you're confused by that, just go ahead and do the fraction addition. So that means that we want it to end at 2 pi by 3, which I will show you as we get further along. So let's just keep putting these values in. So this is going to be pi by 3, and this is going to be pi by 2. And again, if you're confused by this, look at your unit circle. And this is going to be 2 pi by 3. Okay, so we know that at this point, again, this value is back up at the top. Great. And we also know that exactly in the middle, so in this case it'll be right here, it's the exact opposite. Now, determining where they go in between is what usually confuses people. So once you know your middle value, which in this case is pi by 6, and again, you can either figure that out by like literally doing the line distancing if you want. Like this shows it's 2, 4, 6, 2, 4, 6. So you've got that exactly in the middle. And then in the middle of those middles, so from here to here, you want to get that middle value. So in this case, 2, 2, 1, 1, and it's going to be exactly halfway through here, where the thing goes back through the equation. This is kind of a less convoluted way to do this. There is a more complex way, and I'll probably show you guys that next week. I just like to show this way first so that if anyone is like super confused, they can at least just use logic to sketch the graph as accurately as possible. So again, we want halfway through this point to this point. So you could do like 2 here, 2 here, 1, 1, 1 there. So it'll be right here. And that's another flow through point right there. Okay, so here, if I was to put this all together, whoop, let's fix that. That is one period of this function. Okay, again, the steps that we used are a little bit different than what you would be taught in class. In class, they expect you guys most of the time to kind of figure this stuff out intuitively on your own. I personally don't think this is something that one can just automatically intuit if you haven't had tons and tons of practice or lots of examples. So that's why I like to do it this way. So again, the steps are here. Start at the phase shift. And if you know that it's a cos function, obviously you start at the top of the amplitude situation. If it's not a cos function, it's a sine function, you would start at the C, or the middle. In this case, the middle is 0. So if it was a sine function, we would have started at 0. And then you go on from there. So this at least allows you to draw one period. Sometimes teachers will want you to draw 2 periods, and that's fine. If you want to draw another period, you can figure out what the next period is going to be by going 2 pi over 3 plus pi, because the period is pi. And obviously this can be changed into 3 pi over 3. So overall this is going to become 5 pi over 3. So over here, you'll get to 5 pi over 3. Okay? So again, and again, if you're confused, like if you've set up your graph properly, you can literally just keep on trucking. And also one thing to recall is that you can always just look at your unit circle to know what you can put down here. It does obviously get more complicated as the questions get harder, but it is important to show your steps. And again, oh, sorry, I was yawning and trying to write at the same time. So again, the period is from here to here. That's one period. But we can do that again. And if you know how many blocks you use for one period, so in this case you had 4 here, 1, 2, 3, 4, 5, 6, 7, 8. So you can bring that all together, add another 12 blocks, and just fill in the numbers, and you'll be fine. Like again, this is not as hard as it seems, but it does take some practice. Okay, you guys? So let's take a look here. If I'm gonna pause for a second on my talking and let you guys ask any questions that you might have. And if you're following along and using Desmos, feel free to let me know, because I do approve of Desmos, but don't use Desmos as a crutch. Use Desmos as a way to check your answers, okay guys? Not as a way to like in exchange, or in the place of, I meant to say, actually doing the work. Alrighty. Okay, you guys, let's try another example. I'm going to try an easier example just because I like to show this so that when you start with the easier ones, we can build our way up, but that at least you have a framework for understanding what we're talking about. So let's take a look here. Drag and drop this bad boy. Like that. Just as such. Ugh. I want them to be more square. Which is hard to do when you don't have the space to drag and drop properly. Okay, whatever. You guys can see that that's enough space. Let's just put some lines on this bad boy. Great. So, we've got this like this, and this like this, and just go this way, this way, this is Y, this is X. Okay. So let's say, for example, we have been given the question, graph the value, or graph the graph. Graph the function is what I'm trying to say, you guys. Sorry, I'm very tired. Graph the function of 3 sine 2 theta. We can definitely do that. That's not a problem. First things first, what I want to determine is always the amplitude. If it's been given to us, we know that it is 3. And in this case, if we're breaking this down into what we have been given and what we haven't, we have a k value of 2. We don't have a c value. We don't have a d value. So there's no phase shift and there's no vertical shift, which means that we can just go ahead and solve some other stuff. So if we've got a k value of 2, we can solve for our period by going period equals 2 pi divided by 2, which equals pi, which we know all about that, so that's no problem. Now again, sine functions always start at 0, 0. So I'm just trying to show you guys the original sine graph that we did. So remember that the sine graph started at 0, 0. And we know that that information is helpful to us because we know that in this case, this sine graph can also start at 0, 0. Before I keep moving on though, I do need to fill in a couple things. So remember, there's no phase shift here. So if technically, because there's no phase shift, we're just starting where the graph usually starts, which again is at 0, 0. And then we're going all the way to the period. So in this case, the period is pi. So I'm going to split that up like such. I'm going to have, we're going to split it into 4, but I'm going to make these a little bit wider than they are. So 1, 2, 3, 4. So this is pi. This is pi divided by 2. This is 3 pi by 4. And this is pi by 4. So in this case, the graph of the normal sine function, which would have gone to 2 pi, which we can illustrate that as well. So actually we super can't because 2 pi is over here in this case, but you guys get what I'm saying. You're picking up what I'm putting down. This is 3 pi by 2, so on and so forth. Anyways, point of the story is that this particular graph that we're talking about goes to pi because the graph has had a horizontal compression. And the way that we can know what to do, again, is just remembering our normal sine graph going to 2 pi. It still follows those same rules though. Like if normally on the sine graph, usually it goes through 0 again at pi, well now this is going to go through at 0 again at 2 pi, or pi by 2. And then here, hold on one second, there has been a vertical stretch, so this is going to go all the way to 3 and -3. Oh, that should be there. So this is negative 3. So again, this is going to go all the way up to 3, all the way down to negative 3, and because we know that it has to come back to pi, and we know that how the original graph looks, oops, let's try that from the beginning, as some people say. It's actually a really funny video of a guy trying to say the beginning and he says the beninging over and over again. A personal fave. I am a person of high quality taste like that. You guys know how it is. Okay, so this is one period of this graph. So this is y equals 3 sine 2 theta. Let's compare this to what the original sine graph looks like. So the original sine graph only goes to 1, and we know that at pi by 2 it's at 1, and here it goes through the graph again, and then here it goes here, and so on and so forth. So if we're comparing what these graphs look like, it's actually quite a significant difference, if you see what I'm talking about. Pretend that line is nicer. So this is y equals sine of theta. So this is one period of y equals sine of theta, and this is one period of y equals 3 sine 2 theta. And it's really good to kind of compare these in concert, like with one another is kind of what I'm getting at, just so that you can grasp really what's happening. Because again, this got compressed by a factor of 2, which means it's now takes half the amount of time to accomplish the same goal. And you can see that because where it originally ends at 2 pi, it's moved to pi. Where it originally is at pi, it's now at pi by 2. So everything has been divided by 2, which is important to note. And then also the amplitude has been lifted, which means there's a vertical stretch. And yeah, so you guys, it takes quite a lot of time to do like a full graphing question, so I won't subject you guys to one more of these, but next week we are going to continue with this lesson because there's just so much to this unit, and it's important that we kind of do all the different aspects so that everyone can get a good understanding. But if you have questions for me, feel free to drop them in the chat before we go. And if you have questions that you want me to address next week, you can send them to our email address, which I will put here. It is admin@scholarlyelite.com, and we can, the team and I will collect the questions for next week as we always do. And, oh, there we go. And we'll address that next week for you. Okay, guys? So other than that, if nobody has any questions, I'm going to log off, but I wish you all a wonderful week of distance learning and just of being a person. And I hope that you have a wonderful day and a great weekend. Stay safe. And if you ever need anyone to talk to, please feel free to go to kidshelpphone.ca. It's an amazing resource, and there are some great people there to help you guys out. But if you need someone to help you with math, then feel free to reach out to us. We have online tutors working around the clock, or you can send in a message and we can address your question during next week's freemathhelp.ca. So have a great day, and I'll talk to you guys soon.